Hi, this is part 2 of matrix inverses and systems of linear equations. We're in the process of calculating the inverse of a matrix. So we are in the process of calculating A inverse, here assuming that B denotes A inverse. And what we're using, even though we don't know what B is, that's what we're going after. We're using the information, the fact that we know that A multiplied by B equals the identity, and we have used this in order to convert this information we know, which is a matrix equation, into a series of vector equations with a very specific format, vector equations that are familiar to us as linear systems of equations with A as coefficient matrix, and vector of constant. The vector of constant changes in every scenario, but is the standard unit vector, one of the columns of the identity matrix. And so with that at hand, we are able to compute columns, each of the columns of B, and once we accomplish that, then we would have all columns of B, we have B, and therefore we have the inverse of the matrix. So what we were discussing last was precisely what I just mentioned. So we have the problem in which we consider a linear system with A coefficient matrix of coefficients, E1 for the case of the calculation of B1. We use the standard unit vector, first column of the identity, and this is what we have. So we form the augmented matrix. So notice that here this column, so notice that in this augmented matrix we have the last column is the vector of constants, which is in this case the first column of the identity matrix, the standard unit vector E1, and then the matrix of coefficients is the matrix A. So we form this augmented matrix, draw reduce it, and find that indeed there is no leading one in the last column. This system is consistent. The solution set would be a solution set that has only one vector, and that vector is precisely the vector in the last column of this the RREF of the augmented matrix for this problem. That implies that that vector that we didn't know, the vector B1, the vector variables or unknowns, now we do know that vector is exactly equal to the last column of the RREF of the augmented matrix. So we could do this sequentially. So we change this to compute B sub 2, then we're interested on the linear system with A as coefficient matrix of coefficients and E2 as the vector of constants. And by solving that system, notice that this looks very similar to the previous augmented matrix, but it's not quite the same because now the last column is E sub 2, not E sub 1, but is similar, is consistent in the way in which this looks now. This is for a solution set that contains only one solution and one solution only, and that solution is this, and that's precisely the value of B2. So we can repeat this sequentially. For B3 we use the vector E sub 3 and then obtain B3 in this way, and then for B4 use the vector E4 and do the same as using the vector E5, and that would lead to the following calculation of the vector B5. So in this way we have computed columns of a matrix that were unknown, and we have computed one column at a time by means of calculation of solving linear systems, right? So when we're using RREF here, we're intending to come up with a solution set of a smaller sub-problem, and we're coming up with our calculations for each column and in this way. So in summary, we would say that the columns of B, here they are. This is the matrix B, which is precisely this would be what we call the inverse of A, right? So B is the matrix that has the property, this is exactly what we're using here, that A times A inverse equals the identity, right? So you could pause the video right now, click pause, and you could take this matrix as an exercise, take this matrix, multiply that matrix. You should verify that A times A inverse equals I, and also do the multiplication using A inverse on the left side, A on the right side, and then verify that that is equals I. That is equal to I. So now we can continue on the methodology for calculation of inverse of a matrix. And this is summarized in this theorem. If we were going to do, instead of doing the calculation of one column, each column of the inverse, one at a time, we could compute the entire matrix at once. So what we were doing before was augmenting the matrix, right? We had A, and A was augmented with each standard unit vector of each column of the identity, and then we were row reducing, right? So RREF, and this was giving us this was leading to what we know as the columns of the matrix we're going after. But look at the shape here. So we're assuming A square. Okay, we're assuming A square, and then that was augmented by a column vector, and then that was being row reduced. So now what we're going to do is that we're going to consider an augmented matrix, but this new augmented matrix would be an augmented matrix of matrices. So we're going to stack together. Here's the matrix A, and here's the matrix we call I, okay? And by putting them both together, we now have each of them square. Each of them has n rows and columns, n rows and columns. But by stacking them next to each other, augmenting the matrix, not just by one column, but augmenting it by a whole matrix, now we have a rectangular matrix that has, this still has n rows, but now it has 2n columns. Okay, so this is now a rectangle made of two squares put next to each other, group next to each other, and that's what they now call an augmented matrix of matrices, if you will. And we're going to say that what we want is to row reduce this whole rectangle. So if we do this, the theorem says create a matrix M, placing the identity to the right of A. So here's the matrix A on the rectangle, and here is the matrix I. This says place the matrix I to the right of A, and now N would be the RREF of, so basically this whole new matrix is what the theorem is calling M, and now the idea is that this will be row reduced, RREF, and so the matrix M row reduces to capital N, and in addition we say that J is the matrix form and the final n columns of n. So now we want to think of the RREF of this rectangular matrix. We want to think of that RREF, okay, we want to think of this as also a rectangle that is made by two square matrices next to each other. And this is noticing that we want to think of J as the matrix formed by the final n columns. So here would be the matrix J. So the question is, what is here? Okay, so the theorem assumes that A is non-singular. If A is non-singular, then what appears on this portion of the RREF will be indeed the identity matrix. So let's see this more concretely. Here we have a matrix B, and we augment, so this is the first square, right? And then we augment that square with another square, which is the matrix I, the identity. So here's the matrix B and the matrix I, and so now the idea would be to row reduce, compute the RREF of this rectangular matrix. Okay, and let's see what we obtain now. This is row reducing to this matrix, and you can see how in this case this is row reducing, and this square here, this is the matrix that we call the identity, and then this matrix here would be the matrix we were calling J on that theorem. Okay, and so what we're finding, basically we're saying that we have B augmented with I. This forms an original rectangle. This is what we're calling M, and that row reduces. This is the RREF. That row reduces to something that looks like I and augmented with J, right? It row reduces to another rectangular matrix. We started with I on the second square, but now I appears as the first square. And so this matrix that appears here that we're calling J, which is this submatrix, that matrix would then be the inverse of the matrix we're interested in. So in this case, this matrix J is no other thing than B inverse, the inverse of the original matrix. So this is a straightforward algorithm or method. It relies entirely on row reduction. You're given a square matrix, augment that matrix with another square, and now you have a rectangular matrix, row reduce, and then look at the RREF, identify where you have the identity, and you'd be working with the other piece. So if a square matrix has an inverse, then we would say that that inverse is unique. This is a theorem. We have a few theorems here. Let's see. If you have a matrix with an inverse, we would say it is invertible, and the inverse of the inverse is the matrix itself. Here is where you may think that you could mix this with the operator of transposition. If the matrix is invertible, then the matrix and its transpose are both invertible. So A is invertible, A transpose is invertible, and you have there that the inverse of the transpose is the transpose of the inverse of the matrix. That's also a nice property of concerning the scalars. The inverse of a scalar multiple is equal to 1 over alpha, where alpha is a complex number, times the inverse of the matrix.